Hi class, this is Mrs. Lyons. We are starting into the information in Chapter 2. This lesson covers significant figures, and significant figures are going to stay with us throughout the entire rest of the school year. So this lesson is something that is very important for you to get the concept of right away, and if you don't get it, to keep working on it. When we talk about significant figures, we're talking about a measurement and the measurements that we make to use calculations. And anytime we make a measurement, there's a degree of uncertainty. There's a digit in every number that corresponds to a measurement that's estimated. Okay? And this estimated digit is called uncertain. Okay? A measurement always has some degree of uncertainty, okay, and we're going to get into measurements later in the week and you'll see what we're talking about. The reason for this uncertainty is that measurements are performed with instruments, and there's no instrument that can read an unlimited or infinite number of decimal places. Every instrument has limitations to how specific a reading it can give, whether it's a ruler, a graduated cylinder, or an electronic balance. Two terms I want you to be familiar with are precision and accuracy. When we talk about measurements, it's important to differentiate between these two terms. Accuracy refers to the agreement of a value with the true value. So, for instance, if I give you something to measure and I know that whatever you're measuring is exactly 2.1 centimeters, if you make an accurate measurement, you would also get a reading of 2.1 centimeters or very close to that. Precision refers to the degree of agreement between several measurements that are made in the same way. So, for instance, if you and your lab group measure that, say you measure a piece of chalk, and you all measure it to be, your measurements come out approximately the same or very close to each other. Your measurements are precise, okay? We said there's precision in those measurements. Now what we're going to find out is that a measurement doesn't always have to be accurate and precise at the same time. So we're going to use archery as an example. We're going to talk about the accuracy and precision of the shots that an archer makes. Okay, in this first example, 3 arrows, we know that the archer is shooting for this center red bullseye. Okay, this person didn't hit the bullseye at all, so the shots are not accurate. They are way off target. Not only that, but they're very spread out. So these shots are neither accurate nor precise. In this example, the archer shoots all 3 arrows right in the same area of the target. Okay, so they've got precision to their shot. They're hitting the same spot every time. However, they're not accurate because they don't hit the bullseye. Finally, our last shooter actually hits all 3 arrows right in the bullseye, close together on the mark. So these shots are both precise and accurate. Now, if we apply this to the lab, let's say I have measured, let's say, a piece of chalk, and my measurement says that the chalk is 7.23 centimeters in length. Okay, you and your lab partners go back to the lab, and each of you measures that piece of chalk. One of you says that the chalk is 7.24 centimeters. One of you says it's 7.22 centimeters. Another one says it's 7.23 centimeters. Okay, these measurements are all very close together. Okay, so they are precise. They're within a hundredth of a centimeter of each other. However, not however, they're also, if you look at the real measurement, 7.23, they're also accurate because they're very close to the actual true measurement. So these measurements would be both precise and accurate. Now, the reason we talk about this and what we're going to get into is oftentimes we look at the numbers that correspond to measurements and we look at the digits. And it gets really important when we're making calculations that our calculations represent the accuracy and precision of our measurements. So we're going to talk about something called significant figures. And significant figures refer to the number of digits in a measurement that are measured exactly, okay? And then one digit of uncertainty. A couple of abbreviations you'll see. We may refer to these as sig figs as an abbreviation. You may see me abbreviate even farther to SF on papers if you have issues with your sig figs. So we need to count how many digits in a measurement are exact. Okay, so we're going to look at numbers that are zeros and numbers that are not zeros. First of all, we're going to look at non-zero integers. So in other words, if we have a number like 234 or 1,896 or 25, all of the digits in these numbers are non-zeros. So they all count as significant figures. So we're going to be counting digits. How many digits in this number are significant? So in this case, 1, 2, all 3 digits are significant because they're not zeros. In this number, 1, 2, 3, 4, because there are no zeros. 3,456, there are no zeros in this number, so this number has 4 significant figures. Now, non-zeros are easy. They always count as significant. When we get to zeros, we have to start defining what our zeros are and looking at which ones count and which ones don't. The first zeros we're going to define are leading zeros. Now, when I'm talking about leading zeros, I'm talking about zeros at the beginning of a number. Okay? So numbers like this, these zeros at the beginning of the number are leading zeros. And as it turns out, we call these zeros placeholders. They do not count as significant figures. So if we want to count the significant figures in this number, these zeros don't count. These 3 non-zeros do, so this number would have 3 significant figures. Again, this is a leading zero, it does not count. This number also has 3 significant figures. If we look at 0.0486, leading zeros do not count as significant, so this number has how many? 3 significant figures. Let's look at another kind of zero. Captive zeros. Okay, captive zeros are zeros in the middle of a number. Okay, so zeros like this, in between 2 non-zeros. Captive zeros always count. So this number, if we count, we know that the non-zero digits are significant, but then this captive zero counts, so this number has 3 significant figures. This number, the non-zeros count, the captive zeros count, this number has 4 significant figures. What about 16.07? We know the 1, the 6, and the 7 count because they are non-zeros. This 0, because it's captive, it's between 2 non-zeros, also counts. So this number has 4 sig figs. Finally, we're going to talk about trailing zeros. Okay, so we've got leading zeros, captive zeros, and trailing zeros. There are 2 types of trailing zeros. Okay. And we need to define our trailing zeros. This is where questions come in, or where we have problems, because Sometimes we have a decimal in our number and sometimes we don't. Trailing zeros are always the zeros at the end of a number. They count as significant only if there's a decimal present. Okay, so in this case, there is no decimal present, so these zeros don't count as significant. This number only has two significant figures. In this number, there is a decimal present, and that means that all 6 of the digits count as significant because this decimal is there. This decimal tells us that we made a measurement, and whatever instrument we were using to measure gave us out to the hundredths place that was correct in the measurement, was certain. Alright, so let's look at 9.300. Again, it's got a decimal present, so that means that all of the digits are significant. It has 4 significant figures. This tells us that whatever scale we measured this on measured out to the thousandths place. One last thing we need to talk about is exact numbers. Exact numbers have an infinite number of significant figures, so we're not going to count them when we do calculations. And by exact numbers, what I'm talking about is anytime I give you a conversion factor, those numbers are exact. Okay, we don't say that this number only has 3 sig figs. We don't say this number only has 1 sig fig. We say that it's infinite because it's a conversion. And I'll show you how that applies later on when we get into conversions. Alright, just a little helpful trick that I think is very useful in remembering how to count these zeros. If you envision a U.S. map, and on a U.S. map we have 2 oceans, one on either coast, the Pacific Ocean on the west, the Atlantic Ocean on the east coast, and you're thinking, what in the world does this have to do with chemistry? However, it's just a neat little trick. If you remember Pacific starts with P, and then remember present also starts with P. Atlantic starts with A. Absent also starts with A. And when we're talking about present and absent, we're talking about the decimal in the number. Is the decimal in the number present, or is the decimal absent? For example, a decimal present would be a number like this. Okay, there's a decimal present. A decimal absent might be a number like this, no decimal. Okay, so how does this help us count significant figures? If the decimal is present in the number, we start counting our digits from the Pacific side, or the west side of the number. As soon as we get to our first non-zero, everything counts. So since this number starts with a non-zero, we count this and every single digit after it as significant. So this number has 1, 2, 3, 4, 5, 6 significant figures. Over here, the decimal is absent. There's no decimal in this number. So I should have another 0 here. Okay, no decimal in this number. So we're going to start counting our digits from the Atlantic side of the number, or the east side, and we're not going to count anything until we get to a non-zero. So all of these zeros don't count. We start counting once we get to the first non-zero, and then we count everything after that. Once you start counting, everything counts. So this number has 4 sig figs. Let's look at another example. Let's say we have 0.0120. Alright, first thing we say is the decimal present or absent. In this case, the decimal is present, so we're going to start counting our sig figs from the Pacific side. We don't count any zeros. Once we get to the first non-zero, we start counting. So 1, 2, 3. This number has 3 sig figs. What about 20.010? Alright, again, there's a decimal present. We start counting from the Pacific side. We start with a 2, so that's not a 0, so we count that and everything after it. So 1, 2, 3, 4, 5. 5 sig figs. One more example with the math, and then we'll do some more practice. Let's say we have 20,420. All right, no decimal in this number, so the decimal is absent. We're going to start counting from the Atlantic side. Zeros don't count. We start counting with our first non-zero, count everything after that, so this number has 4 sig figs. Alright, so let's practice. How many significant figures? First thing we do, the decimal is present, so we start counting on the Pacific side. The 1 is a non-zero, so we start counting with the 1, count everything after that. So we have 5 sig figs. All 5 digits are significant. What about this number, 17.10? Again, decimal present, start counting on this side. Since this isn't a 0, everything counts. 4 sig figs, all 4 digits are significant. 100,890. No decimal, so decimal is absent. We're going to start counting from the Atlantic side. We don't count the 0. We start counting at the first non-zero, and then we have 1, 2, 3, 4, 5. 5 sig figs. Those 5 digits are significant. Alright? This one is scientific notation. Looks a little tricky. It's really easy. In scientific notation, you just look at the base number. You completely ignore the exponent. So in this number, all 3 digits are non-zeros, so there are 3 sig figs. Easy stuff. Next one is the decimal present or absent. It is present. So we start counting from the Pacific side. We don't count the zeros. We don't start counting until we get to the first non-zero. Then we count everything, so 2 sig figs in this number. One more. 3,200,000. No decimal. Decimal absent. So we start counting from the Atlantic side. We don't count any zeros until we get to the first non-zero. 2 sig figs, the 3 and the 2. Alright? Now that we've been able to count, we can look at a number and tell how many sig figs. The important thing is that when we do calculations, we need to be able to account for the significant figures of our measurements. Okay? Every time we do a calculation, it's going to be based on a measurement. Whether we've done that measurement in the lab or someone else has done the measurement and gives us the numbers. And there are specific rules for multiplication and division and addition and subtraction. Multiplication and division is the one that is easiest to me and the one that we'll use most often. In multiplication and division, the number of significant figures in the answer is equal to the number in the least precise measurement. So what we do is we have, these are our measurements, 6.38 times 2. We want to carry out this mathematical operation. What we're going to do is we're going to look at how many significant figures are in this number. 1, 2, 3. And in this number, decimal present, we're going to start at the Atlantic side. There are 2 sig figs. So our answer can only have the same number of sig figs as in our least precise number of our measurement. This one is least precise because it's only got 2 sig figs. So our answer can only have 2 significant figures. If we plug this into our calculator, we get this answer. We need to write this answer with only 2 sig figs. So this digit and this digit will be part of our answer. That's 2 sig figs. But we need to look at the digit, the first digit that we're not including, and in this case it's a 7. Since it's a 7, rounding rules say if it's 5 or greater, we round up. So instead of 12, our answer would be 13 based on the rounding rules. Okay? So that's how we look at multiplication and division. Let's do a couple of examples, and I'm going to leave you with a few to do to bring back to class with you. Okay? 3.24 times 7.0. This number has how many sig figs? 1, 2, 3. And this number has 2 sig figs. So the least precise measurement is 2 significant figures. If we plug this into our calculator, we get this for an answer. We can only have 2 sig figs in our answer, but we have to look at that next digit for rounding. Since it's greater than 5, we're going to round up. Our answer is going to be 23. And we'll talk about units, but notice that we multiplied our units. So meters times meters is meters squared. We always want to include a unit when they're given. Here's another example. 100 grams divided by 23.7. Same rules apply to division. Okay, so this number has how many sig figs? Decimal present, start counting over here. 1, 2, 3, 4 sig figs. This number has 3 sig figs. So when we plug this into our calculator, we get this long answer. We cannot write that answer because that makes us think that our whatever tool we use to measure measured out to this many digits. That's not true. Our measurement only measured 3 significant figures, so we have 3 sig figs in our answer. 4, 2, 1. We have to look at this 9 for rounding purposes. Since it's greater than 5, we're going to round up. So 4.22 grams per centimeters cubed is our correct answer. Alright, I want you to take a look at these calculations. I'm not going to put the answers up in the correct number of sig figs, but I would like you to go through these and look at them, count how many significant figures in each measurement, determine how many significant figures should be on our answer, and write down answers for significant practice number 2. When we come to class, we will take a look at these together. Okay? There's one more. So pause the video. I'm not going to take time to go through them, but you go through them and see if you can come up with the answer to the correct number of sig figs, and we will look at this. Alright? Moving on, we need to talk about addition and subtraction. And the rules for addition and subtraction are a little bit different. Okay? Instead of counting the least precise measurement, what we're going to do is we're going to count the number of decimal places in the least precise measurement. Okay? So for example, if we have 6.8 plus 11.934, we're just going to look at the numbers following the decimal. Here, there's 1 digit after the decimal. Here, there's 3. Our answer has to be the least number of decimal places. So, if we do this in our calculator, I wrote on it, but our answer comes out to be 18.734. We can only have 1 place after the decimal, so our answer is going to be 18.7. That gives us 3 sig figs. Okay, let's look at some more examples of this. And again, we'll do a couple together, and then I want you to finish these for when you come to class. Alright, if we're adding, we're looking at the number of decimal places. So this number has 2 places after the decimal. This number has 1. We plug it into our calculator, we get 10.24. We can have 1 place after the decimal in addition. So that means that since this number is less than 5, we just drop it, giving us an answer over here of 10.2 meters. Alright, in this example, decimal is present. We start counting from the Pacific side. 1, 2, 3, 4 sig figs. This number, oops, I'm sorry. Wrong. We don't look at sig figs. We look at places after the decimal. So this number has 1 place after the decimal. This number has 2 places after the decimal. Okay? It's a subtraction problem. So our answer, when we plug it into our calculator, is 76.27. We can have 2 places after the decimal. So the answer is 76.27 grams with 2 places after the decimal. Let's do one more together, and then I'll leave you with 3 or 4 to do on your own. This number has 2 digits after the decimal. This one has 3. So our answer can have 2 places after the decimal. That means the 3 and the 9 can be reported in our answer, not the 1. Since it's less than 5, we just drop it. So our answer is 2.39 centimeters. There's a decimal there. Okay, couple more examples for you to look at and figure out what the correct answer reported to the correct number of significant figures would be. Okay, do these on your own. We will talk about them when you come to class, and we will do some more practice on counting significant figures and then doing mathematical operations with significant figures. As I said, this is a very important skill. You will use this on every calculation you do from now through the end of the school year. So it's important to get this now and to keep it in your mind and always think about significant figures. Alright, that's it for sig figs. I will see you in class.